Hello, welcome to this video. Today we'll talk about my view, Peppe's view, on convolutional neural network. Let's start from the beginning. What's the definition of convolution? Well, a convolution is an operation that takes a certain function x, function of maybe some variable, then it weights that function x by another function w, and you get another function, a resulting function y. As an example, let's focus the attention on this example. So we start from x. X is a function of t, and then we reweight the function x by the weight function w, and w is a function of I minus t, and we do the multiplication of x times this weight function, and we sum over all the possible t, so basically this becomes an integral over dt. And to visualize things, let's do an example. Okay, so let's imagine that our weight function w here is localized. So let's imagine that it peaks around 0. In this example, the function w is function of z, okay, and w is peaked around 0, and then it sort of vanishes when you go too far away from 0. Okay, so imagine, I don't know, it's a Gaussian, for example. This could be 1, this value, and then let's say that a certain number of sigma away from the mean, this value here is practically 0. Okay, so we have this weight function w localized around 0, for example. Then let's say that we fix a certain I, so I bar, and let's focus on what would be y of I bar. Okay, so that's the idea. We fix I bar and we ask ourselves what's y of I bar. Well, given that we have to multiply x by the function w computed in I minus t, and then we have to sum, okay. Since y is localized, that's our first assumption, y is localized around 0, this weighted sum is non-zero only if t is close by I, because y0, let's say, is 1, and then y of a big number, let's put plus infinite, well, this is 0. So y of I bar is itself a weighted sum of the original function x of t, but the t that actually count are only the t's that are around the value I bar itself. So basically, all of this is a weighted sum of the original function xt with t that are around I bar. That would give you y of I bar. So all in all, it has a smoothing effect. Let's say that the starting x function is this one. So it has a shape that is very not so smooth, let's say. Then we convolute it, and the symbol for convolution is this star symbol here. So we convolute the original x with a certain weight function w. As we said, for each I bar of the resulting function y of I bar, we basically compute an average around I bar itself. And so basically, if we have to compute the average of a value that is around here, well, we pick some values. Let me change color. So let's say that this is our I bar. We pick some value here in this region, some y here on this region. And so basically at the end, we smooth this sharp shape here, and we get at the end something that is smoothest. So that would be the resulting function y as a result of the convolution of the original not smooth x convoluted with a weighted function w. That's a bit what a convolution is. Then, since we are going to use it in machine learning, we are going to use it on computers, well, we don't really do the integral, we do a sum of a certain number of points. And so the integral becomes a sum and a finite sum. So our y is basically a weighted sum of our original x function by a certain weight function w. So now we jump directly into neural networks. Let's say that we have some weighted sum of the original inputs x con I, those are our features. We weight them using some w's, some weights, and let's say that the ensemble of all the weights that we used, we can organize them, imagine in a matrix or a tensor, we can call it filter. Okay, we compute this average weight with this weighted average, then we pass an activation function, we apply the activation function on the weighted sum that is normally called A, and as activation function we can imagine a ReLU, a sigmoid, these kind of things, and we get what is normally called Z, a variable called Z. Let's give a visual step, what I'm talking about. So let's go in one dimension. Let's do an example of convolution. So we start from, okay, let me pick yellow. We start from those features. So those are our initial features, okay? And let's say that we want to apply a filter of dimension 3. So what do we do here is that we start from this point, we combine the first 3 using the weighted sum, and so we weight this feature by W1, this feature by W2, this feature by W3, and we get a certain thing, and then we apply an activation function on this weighted sum. And then we sort of shift everything, and so we take this other 3, we do the weighted sum, and we use again W1, W2, W3, the same one as before, on this other 3 inputs, and then we shift again, we use these last 3, and we weight those last 3 inputs using the same W1, W2, and W3. And this is different with respect to what we would have done using a dense layer, because in that case, let me give you an example. In that case, if we use a dense layer, if those are the initial features, everything is connected with everything else. So, for example, here we have 3 output nodes, so everything is connected. So in total, if we have 5 input features and 3 output nodes, you will see that if you do the calculation, each output node receives 5 inputs. So 3 times 5, you get 15 weights that basically you have to optimize in order to minimize the loss function. Or actually, not you in person, but TensorFlow, PyTorch, whatever tool you are using to minimize the loss function. So basically here you are having 15 weights, so every weight is different here. This is Y1, this is W2, for example, this is W3, and so on and so forth up to W15, while in the previous case, where we used the convolutional approach, well, we are just using 3 weights, and they are always the same weights that have to be optimized. So you have a lot more weights if you use a dense layer rather than a convolutional layer. Now, let's imagine a 2D example, 2-dimensional example of convolution. So we have a matrix as input. let's say that imagine that we have 5 by 5 input matrix and we want to use a 3 by 3 filter. So we use this little matrix, this little blue matrix here, and each entry of the blue matrix, which is my filter, has a certain weight, W1, W2, W3, up to W9, okay? And those weights, Y1, Y2, Y3, up to W9, they will be used to compute the weighted average of the original 5 by 5 input. So basically I take the input inside this matrix and I weight them by this 3 by 3 filter, by the coefficients that are dictated by the 3 by 3 filter that I'm using, and I end up having one single number, this one, okay? This one is the weighted average of this 3 by 3 sector of the original matrix that I have, weighted by the 3 by 3 filter, and so on and so forth. Then for the next one, let's imagine that I shift, okay, I shift by one position on the right, okay, so I do this operation, if you want, I take this original 3 by 3 filter, I shift by one on the right direction, I have another 3 by 3 matrix, I mean, I'm using the same 3 by 3 weights, and I compute another average, and this average goes here. Then I stride again, I shift by one position, okay, like this, and I get this other point, and so on and so forth, and you will see that I organize everything using, again, the same 9 weights, the same 9 weights that are contained in the original 3 by 3 filter, and I have to optimize them. So those are always the same weights that I use over and over again to compute my weighted average. And basically, after I do this convolution, I end up with a 3 by 3 matrix, which contains the weighted average over the original 5 by 5 input that I used. Normally, after a convolutional layer, we mount on top of it a pooling layer as well, typically a max pooling layer with a certain filter. So for example, let's do everything from the beginning. We start again from our 5 by 5 matrix. So this is my 5 by 5 input matrix. Then I apply a 3 by 3 convolutional filter. So the step that we did before, and we end up here. So we have a 3 by 3 matrix, which is the result of the convolution. And then I apply a max pooling layer of dimension, for example, 2 by 2. And actually what I do here is I take this 2 by 2, let's use, for example, red. Okay, I want to use this 2 by 2. I go here. Okay, I inspect this 2 by 2 subpart of the 3 by 3 original matrix, and I take the maximum over all these 4 entries, and this would be the result. Then I shift by 1 on the right, and I obtain this other number, which is the max over this new sector, and so on. Then I shift down, and then I shift right again, and I obtain these 4 numbers here. Okay, so better drawn. Here it's what we did. So we start by the 3 by 3. We apply this blue filter. I apply the max pooling, and then I obtain my 2 by 2 result, which is the result after convolution plus max pooling layer. Normally, what they say is that if you apply a convolutional layer, a certain filter 1, let's say, plus on top of it you apply a max pooling layer, so you have another filter, different dimension, what you do is actually you do a feature extraction. My way of seeing this is that basically imagine that you want to check if an image contains a certain feature, which could be, I don't know, for example, the edges of the features of the original images. you want to detect where in the image you have these edges that you're looking for. So you apply a certain filter that is supposed to be sensitive to the edges of the image. And that's the idea of the first layer, the convolutional layer. And then you check with the max pooling layer if that feature, so the edge, was actually present in that portion of the feature that you analyzed using the filter number 1 of the convolutional layer. That's a bit the idea, but the cool thing is that you don't have to write the explicit code for doing that. So you don't have to write the explicit code to detect the edges of the original image. You let the machine learning thing understand those things by itself. So by minimizing the loss, by minimization of the loss, you end up with certain weights that go inside your filters, so the convolutional filter and the max pooling filter. And the cool thing is that they actually do something. They actually result in feature extraction without explicitly hard coding the feature extraction code itself. So that's a bit the idea of convolutional plus max pooling layer. Now, what are the parameters of a convolutional neural network? Well, you have the number of filters, because it's not said that you want to apply only one 3x3 filter. For example, let's focus on this part only. So let's focus only on the convolutional part. Here we are applying a 3x3 filter on top of a 5x5 input, and so we are obtaining 9 weights by minimization of the loss. It's not said that you want to apply only one 3x3 filter. It's possible that in parallel you want to check for several features. For example, if this is an image, you want to check where are the edges. I don't know, if you are doing image recognition, you may ask yourself if this is a cat, if this is a dog, or something like this. So you want another filter to detect where are round-shaped things. For example, the eyes of the dog or the eyes of the cat. So you want another 3x3 filter whose job would be to be sensitive to round shapes, so eyes. Let's imagine that. And we apply, so in parallel, a certain number of 3x3 filters. And so that's why number of filters is a parameter of this. Then, of course, we have the kernel size. So the dimensions of our filters, for example, 3x3, but doesn't have to be squared. It can be rectangular, so it can be also a 5x3 filter or something like this. That's not a problem. And then this is something that we didn't talk about. Also, stride is a parameter, actually. An hyperparameter of this kind of models. Because, for example, let's say that we start with a 2x2 filter here, so top left. Then we can proceed by 1 on the right. Okay, and we end up here. So this would be stride 1. But we can also jump directly here. And so we do our first average like this, and then if stride is 2 in this direction, we can jump directly here, and then we do this other weighted average. And then we have another type of stride, so we can move in a different way downwards. So for example, downwards, now we can do by step of 1, or we can jump directly by 2, or, well, this is a small matrix, so we cannot do that. We cannot do more than that. We cannot do more than 2, actually. But if the matrix is bigger, it can be 3, 4, etc. So basically, stride is an hyperparameter that tells us how do we move, how do we shift the filters that we are using to detect our features. And finally, we have a padding variable, which can be valid or same. And basically the idea is that if we go back to what we did before, maybe I can give you another example. So let's focus on example number 1. Okay, let me give you an example. Say that we have an input matrix, our image, which has sides 3 by 3 in this example. Okay, so this is the input matrix. We have a kernel, so a filter 2 by 2, and stride is 1, 1. Now, since stride is 1, 1, say that this is our first weighted average. Then we stride by 1 on the right direction. We do another weighted average in this other direction, in this other subpart of the original matrix, and we get this other weighted average. And we do that up to the end, and we end up with a smaller matrix than our original image. You see that this is 2 by 2. And we do that because it happens because we used valid as padding. What happens if we use same as padding? Well, the idea is that we change the input. So this is our input, same input, 3 by 3. We change our input so that we put a border of 0, okay, around it, like this. We change the input dimensions so that when we apply the kernel, we end up doing the weighted average of something that contains 0. Okay, that's true. Then we stride, we do our stuff. Once we complete the convolution, we end up again with the same dimensions of the original image. That's why it's called same padding. So there are cases where you want to keep the dimensions, so you use same as padding, and there are cases when you don't care, so you use valid. That's a bit the idea. Then, a rule of thumb is that it's better to use many small filters rather than one big one and lonely filter. So if we have our original image dimensions n by n, we apply a certain filter, filter 1, the dimension. We shrink the original dimension, so it's not n by n anymore, it's something a bit smaller, and then f2, another filter, and we shrink again, and then f3, and so on and so forth, up until the end. Let's say that we care only about one output, so we go from n by n by making several filters, several steps, and we shrink everything up to the dimensions that we care about. And the rule of thumb is that it's better to have many small filters rather than a big one. So it's better to do this rather than this, when we have only one filter, one big filter, and we end up in the same dimension of the output. So the rule of thumb says that this is worse. Then, of course, since the neural network is deeper, then there are potential problems with the vanishing gradients, but this can be tackled with using ReLU's activation functions. Okay, so now let's jump to the implementation in Keras. Just a few details because I want you to visualize things. So let's meet again on a pseudo Keras environment. Okay, here we are now. Let's say that this is a pseudo Keras environment. Actually, I did my things in Keras, then I did a screenshot, and I basically pasted everything that I had here. So let's say that this is a small convolutional neural network that I implemented in Keras. So I have my sequential part. Okay, then I start adding my convolutional filter. And let's see what happens. I have 32 filters of size 3 by 3. As I said, normally you use ReLU, so to tackle with the vanishing gradient problems. And then this is the input shape because I have images 28 by 28 by 1. And then after I do the convolution, I add the max pooling layer. Okay, now let me remove what I did so that I can keep the black color there. It will be useful for later. Then I do again the same thing, but now I use the green color. So actually, let me use it. This is the green part. Okay, I have again a convolutional layer where I have 64 filters, kernel size 3 by 3, activation ReLU, then I have the max pooling, then I go for a blue part. So I keep doing this, but now let's say that I am at the end, so I do the convolution using 64 filters, and then I flatten everything. So to go in a standard, this is more of a standard feed-forward neural network, this last part here. Okay, and then I asked to Keras to print the summary of my model. So this is the result of basically model.summary. This is what you get if you do this. And there are certain dimensions here that I want you to visualize, and we'll do that together. So basically, for example, after this convolutional 2D layer, so we start from inputs that are 28 by 28 by 1. Those are my images. Then I apply a convolutional 2D layer, and I end up with 26 by 26 by 32. Those would be the resulting dimension after this conv2D layer. So let's see if we can make sense out of those numbers. So this is a bit the idea. I have my image. Okay, let's say that those are handwritten numbers from 0 to 9. The input image as 28 by 28 by 1 because it's not RGB, it's a grayscale. So I have my input image. Then I said that I applied 32 filters in parallel of dimension 3 by 3. Okay, so that's what I do. I do a convolution using 32 filters of size 3 by 3. So I stack one on top of the other, okay, or in depth if you want. And I do 32 filters in parallel. So those are 3 by 3 matrix applied at the same time on this input. So maybe I can draw it like this. So all of these convolution are done together, and maybe that will come later, that will be useful for later. Instead of writing, of drawing all these 32 filters one on top of the next, from time to time, in this example, I can also write the filter, and then I do times 32. This would be my internal notation here. Okay, so if you do your computation, you will see that each time that you apply a 3 by 3 filter with, okay, stride 1, 1 on the original image, 28 by 28, you basically reduce its dimension, and you get a 26 by 26 output. But you have 32 times this dimension because you have applied 32 filters one after the other, or in parallel if you want. So after you apply 32 filters of dimension 3 by 3, you get 32 resulting convolutions of dimensions 26 by 26. Then I have the max pooling star, actually, and that is the meaning of this 26 by 26 by 32 that I find in the model summary. Then I apply the max pooling, and the pooling size is 2 by 2. So the kernel size is 2 by 2, and I did not specify the stride. So by default, in a max pooling layer, the stride is set as the pool size. So the stride would be itself 2 by 2. Okay, so I am here. I have done the convolution. Then I applied the max pool using a stride 2 by 2. So I have 32. This 32 here is automatically computed by Keras. I did not specify it here in the max pooling layer. There is no 32 here because it's automatically computed by Keras in order to match this dimension. So it's applied 32 times. So each of these 26 by 26 convolutions receives a 2 by 2 max pooling filter. And so since the stride is 2 by 2, you basically divide by 2 the dimension. So you end up having 32 matrices of 13 by 13. So after the max pooling layer, I expect that the resulting dimension would be 13 by 13 by 32. And that's why I asked for confirmation by Keras. And that's the case. Okay, now we enter the green part. So let me change the color. So in the green part, we have convolutional layer, and again we have max pooling layer. As I said, the rule of thumb is convolutional max pooling up until the end. Okay, so we have this convolutional layer. We have 64 filters of size 3 by 3. Let's see what happens. So we are here. I continue. So I go down. I recopy the last part. So I have again 33 by 13 by 13 by 32. Then I apply a convolutional. What I wrote there is only 3 by 3. Okay. But since I have 32 matrices, implicitly I am saying that the filter, or Keras is computing implicitly the third dimension of the filter. So you cannot use a filter 3 by 3 only, since you have 32 matrices. So you have to use a filter that is actually 3 by 3 by 32. So it becomes this this thing, this 3D filter, which is applied on all of this. So basically now the thing is that I am doing the average over all the numbers that I find in these 32 matrices. So I am averaging over all the numbers that I can find in this 3D region here. And I am doing it 64 times. Okay, so I start from this. This is my 3D region or 3D filter. Okay, then I stride it. I do everything. And once I have finished, I have my weighted average. So I have my matrix, which has dimension 11 by 11, because we start from 13 by 13 using 3 by 3 filter. So basically we reduce by 2. And after I do this averaging all together 32 matrices, I end up with one matrix which has 11 by 11 as dimension, but I'm doing it 64 times because I have 64 filters. So after I do the convolution by a 3 by 3 by 32, which is implicit calculated by Keras, and I do it 64 times, basically I end up having 11 by 11 matrices, and I have 64 of them. Why 64? Well, because I wrote it, that I want 64 filters. If this number is different, for example, if I put 3 there, well, I have 3 there. Then I have the pool layer, the max pooling layer, size is 2 by 2. From here, I apply 2 by 2. And then this 64 here is again implicitly calculated by Keras, because basically for each of these 11 by 11 matrix, I apply 2 by 2 filters, one after the other, and basically I get, as I said, this is a max pooling layer. Default stride is the same as the kernel itself. So the stride is 2 by 2 in this case. So again, I divide by 2 this dimension and I get 5 by 5, and I get 64 times 5 by 5 matrices. Okay, I reached the end of this green part, and then I come to the blue part. So I am adding 64 filters of size 3 by 3. Let's have a look. So I recopy. So I start fresh. This is 5 by 5 by 64. Then I'm convoluting with 64 filters, and I said 3 by 3. I wrote 3 by 3, and then Keras implicitly calculates the fact that I need 64 as third dimension of the filter. So the filter, actually, the dimension of the filter is actually 3 by 3 by 64. Okay, so again, I am computing averages over this 3D region. I am striding this. So this is another average. This is another average, and so on and so forth. Once I finished, I have one matrix of dimension 3 by 3. And since I am doing it 64 times, and why I'm doing 64 times? Because I specified that I want 64 filters. Since I'm doing it 64 times, I have 64 matrices of dimension 3 by 3. Why 3 by 3? Because I started with 5 by 5. Finally, we have this flattened layer, which basically means, okay, so I have this big stuff here, 64 matrices of 3 by 3. Flatten everything means, okay, transform everything into a single big vector, which would have dimension 3 by 3 by 64, because those are all the numbers that I have in total. I have 64 matrices of dimension 3 by 3. So one big vector, and then I do standard things using feed-forward neural network style. So I'm adding a dense layer, first a dense layer with 64 units, finally a dense layer with 10 units, and basically this part is more common, more standard. So after I flatten things, well then this is standard feed-forward neural network part. I connect everything together with the next layers. And the last layer has 10 outputs, because basically I did that in order to recognize digits, handwritten digits from 0 to 9. So I need four outputs, which are the probabilities that my image is 0 or 1 or 2 and so on and so forth. That's the idea. Okay, so this was intense, at least for me. I hope this helps you basically clarify your mind about this convolutional neural network. So that was my view on the topic. If you liked the video, please hit the subscribe button, leave me a comment, and see you another time.